The deterministic nature of the Casimir effect. A quantum mechanical interpretation. The Casimir effect, a phenomenon predicted by Hendrik Casimir in 1948, has been a subject of intrigue in the realm of quantum mechanics. It is a fascinating display of quantum forces, where the vacuum energy between two uncharged, conducting plates leads to an attractive force between them. While the traditional understanding of the Casimir effect relies on probabilistic vacuum fluctuations, we will delve into a deterministic interpretation, exploring the implications and consequences of a non-random, predictable quantum system. The fundamentals of quantum mechanics. To comprehend the deterministic nature of the Casimir effect, it is essential to revisit the principles of quantum mechanics. In a deterministic quantum system, the Schrödinger equation governs the time evolution of the quantum field, as described by the state vector psi, t. The Hamiltonian operator, h, represents the total energy of the system, and the imaginary unit I, multiplied by the reduced Planck constant, dictates the time evolution. This fundamental framework sets the stage for understanding the deterministic evolution of the electromagnetic field between the plates. Electromagnetic field quantization between parallel plates. The Casimir effect is a direct consequence of the electromagnetic field quantization between two parallel plates. The boundary conditions imposed by the plates constrain the allowed modes of the field, which can be expanded in terms of orthogonal modes. Each mode is characterized by a polarization vector, epsilon, a time-dependent amplitude, a, t, and continuous wave numbers in the x and y directions, kx and ky. The frequency of each mode is determined by the plate separation, L, and the wave numbers, as described by the equation nk, x, k, y equals c square root, n L, squared plus kx squared plus ky squared. Deterministic evolution of field modes. The Hamiltonian, for the electromagnetic field, is a crucial component in understanding the deterministic nature of the Casimir effect. It can be written as the sum of the energy of each mode, with the creation and annihilation operators, A and A, representing the energy of each mode. The zero-point energy of each mode is also included, which is a fundamental aspect of quantum mechanics. The Schrödinger equation governs the deterministic evolution of the field state, with the Hamiltonian operator dictating the time evolution. This deterministic evolution is the cornerstone of the Casimir effect, as it leads to the emergence of the attractive force between the plates. Vacuum energy calculation. The calculation of the vacuum energy between the plates is a critical step in understanding the Casimir effect. The zero-point energy of each mode is summed over all modes, with the plate area, A, and the wave numbers, kx and ky, integrated over. This yields the total vacuum energy between the plates, inside. For comparison, the vacuum energy in free space, outside, is also calculated, allowing for the determination of the Casimir energy, EC, as the difference between the two. The regularization and integration of the energies result in the well-known equation EC equals squared car, 720 L cubed, which describes the attractive force between the plates. Deterministic force calculation. The Casimir force can be calculated as the negative derivative of the energy with respect to the plate separation, L. This yields the equation Fc equals squared car 240 L, which is an attractive force between the plates. This deterministic calculation is in stark contrast to the traditional interpretation, which relies on probabilistic vacuum fluctuations and statistical averages. Comparison with traditional interpretation. The deterministic interpretation of the Casimir effect offers a fundamentally different perspective on the phenomenon. In the traditional view, vacuum fluctuations are random and inherently probabilistic, with Heisenberg's uncertainty principle allowing for virtual particles to temporarily violate energy conservation. In contrast, the deterministic interpretation relies on the deterministic evolution of the electromagnetic field modes, with the boundary conditions imposed by the plates constraining the allowed modes. This leads to a predictable and deterministic energy difference and resulting force. Philosophical implications. The deterministic interpretation of the Casimir effect has far-reaching implications for our understanding of quantum mechanics, and the nature of reality. It suggests that quantum systems evolve deterministically, with properties such as position and momentum not having definite values prior to measurement. The probabilistic nature of measurement outcomes arises from the interaction between the measuring apparatus and the quantum system, rather than from intrinsic randomness. Heisenberg's uncertainty principle is reinterpreted as a mathematical constraint on conjugate variables, rather than a statement about intrinsic indeterminacy. Conclusion. In conclusion, the deterministic interpretation of the Casimir effect offers a coherent and comprehensive understanding of the phenomenon. By relying on the deterministic evolution of the electromagnetic field modes, the calculation of the vacuum energy, and the resulting force, we can gain insight into the fundamental nature of quantum mechanics. This interpretation has far-reaching implications for our understanding of reality, suggesting that quantum systems evolve deterministically, and that the probabilistic nature of measurement outcomes arises from the interaction between the measuring apparatus and the quantum system. As we continue to explore the intricacies of quantum mechanics, the deterministic interpretation of the Casimir effect serves as a beacon, illuminating the path towards a deeper understanding of the quantum world. Word count, 1030 words. Note: the provided content is an article-length essay that explores the deterministic nature of the Casimir effect. The piece is structured to provide a clear and concise explanation of the phenomenon while delving into the philosophical implications of a deterministic quantum system. The language is engaging and accessible, making the content suitable for a general audience interested in quantum mechanics and its interpretations.